start off with resolving power, this is the part or the new concept where we have started. Now, resolving power basically gives you the ability to physically separate the objects as two distinct objects. Now, this is based on what type of optical instrument we are using. Typically focusing on the aperture. Aperture means the size of that particular lens or the mirror and the wavelength of that particular light which is being incident. Now, I already have given you an example. What do you mean by resolving or resolution? If there is a friend of yours, one friend who is showing you two fingers like this, and he's, let's say, standing maybe 10 meters away or even 1 meter away from you. So at this distance, you will be able to recognize the two fingers. But if, let's say, there is another friend who is showing you the same two fingers, but now that particular friend, he is, let's say, 1 kilometer away from you. Now, obviously, you won't be able to identify which fingers or how the pattern it looks like in this particular case. You will be able to see that the person has raised a hand, but you won't be able to actually see the fingers. Why? Due to the difference between the distances. So this means that we are not able to resolve. So here it is not resolved and here it is well resolved. So the first case we consider it as a well resolved objects, and this is the case which we consider as not resolved or unresolved objects. So this is the part which we have seen. In this case, there are three things which we need to remember. First thing is about visual angle. We already know what is a visual angle. It is angle subtended by the eye, which leads us to the limit of resolution. The limit of resolution means the minimum visual angle between the objects which can be resolved, and the reciprocal of that, it gives us the resolving power. Now, this particular concept has been used by Lord Rayleigh and given us the Rayleigh's criteria for limit of resolution, and obviously leading us to the resolving power. So these Rayleigh's criteria, that is what we have seen. The main gist of it is that the limit of resolution, it depends on the diffraction pattern of the two objects which needs to be resolved. And based on this diffraction pattern, we get the condition where the resolution has just started, giving us the condition we call it as the just resolved condition. This is the part where that particular instrument has just started separating two objects. We have already seen these conditions over here, A, B, and C. If we consider A, it is unresolved. So you can see this is the diffraction pattern of these two objects. But obviously you can see, we know that there are two objects, but from this diffraction pattern, we are not able to see whether it is one object or two objects. So you can see that the maximas are very closely spaced. So this is unresolved. Just resolved. Now here you are able to identify, no, yeah, this is not one object, but these are two objects. So you can see that they have just started separating. They just started resolving. We call it as just resolved, just about to be separated, the starting point. But what we need or what we want is this condition. You can see that the objects are distinctly visible, giving us a rise to well resolved case, ideally, which is required. But obviously, whenever we consider of resolution, we need to start at some point. And what is the starting point? This is the starting point, just resolved case. So obviously, while deciding any criteria, we start for this particular point. So now let's apply this Rayleigh's criteria for the different conditions, typically for different types of objects which we have. Now, in case this gives you again the idea about what exactly do you mean by fully resolved or well resolved and unresolved. That two distinct objects are obviously visible distinctly, whereas here they are not visible distinctly. So now moving forward with release criteria, now we are going to apply this for two linear objects. Now two linear objects, just like I told you, we start at the point where it is just resolved. So what we consider two linear objects as two slits. But keeping in mind these two slits, they act as a source of light. That's why we have two self-illuminous or self-luminous objects, which are slits. And obviously we know that they are not very close, but they are separated by certain distance. Now, when they are separated by the certain distance, we know where to start. We start at the condition of just resolved. So when the condition is just resolved, what we know, this is the condition which needs to be achieved. Now, what is just resolved condition? That the first minima of that particular diffraction pattern is the one of the sources which should coincide with the central maximum of other. So here you can see that this is the central maximum of other part, and at this point first minimum of second coincides, so means they just started separating. Or we can look that in the graph as well. Let's say this is the second object which we have, so this is the central maxima, and this it coincides with the first minima of first object. So that is the condition which we know. So based on this particular condition, we can write the angular separation or the angular position of the first principal minima. हम लोग कैसे देते हैं? It is given by this particular formula d theta, which is lambda by a. Theta is lambda by a. That is what we have seen previously when we went for diffraction. D theta मतलब क्या? It's a difference. Small part है, इसलिए d theta लिया है, बाकी कुछ नहीं किया. Now what happens? This is the minima of first object. Now that minima, it coincides with the central maxima of other. Okay. So once again, this is first object, this is second object. ये first object का minima है यहाँ पे. It's coinciding with this central maxima पर किसका? Second का. So since the minima is coinciding with the central maxima, what we have is the minimum angular separation. Now this minimum angular separation can be considered as a limit of resolution. Okay. So this minimum angular separation can be considered as limit of resolution, which can be given as d theta upon lambda by a from this formula. Once again, what happens? As minima is coinciding with central maxima, the separation between them is minimum. The angular separation between the two objects. मतलब क्या? That is what limit of resolution is there. No? The smallest separation possible so that the two objects are distinctly visible. Therefore, the limit of resolution is given by d theta, which is lambda upon a. Now, when we consider the minimum separation, now these are at just resolved case. So at just resolved case, the minimum separation at a distance d from the instrument. Assume karo that this particular objects are kept at a distance d. So what will be the minimum separation in that particular case? Then it can be given by this formula y, which is equal to d into d theta. Once again, this is the minimum separation when these objects are very close to the optical instrument. But what if they are kept at certain distance d? We have to consider the d as well. So limit of resolution will be d into d theta. But what is d theta? Lambda by a. So that is why we get d lambda upon a. Clear? And this is the distance of the first minimum from the center. Any doubts till this point? Bolo re yes or no? Others? प्रथमेश, ईश्वर, कल्याणी, किरण. किरण का है मैसेज? Last 2 points. This one and this one. Okay. Once again, what do we have? ये angular separation मिला. Now this angular separation मतलब क्या? Position in simple words. किसका है? ये first minima का है. बट अभी क्या है? ये first minima coincide हो रहा है central maximum से. मतलब central maximum का position भी क्या होगा? यही होगा ना? Means the position of first minimum and central maximum they are same. तो अगर ये फर्स्ट मिनिमम का पोजीशन है तो यही पोजीशन सेंट्रल मैक्सिमम किसका? सेकेंड का रहेगा. और लिमिट ऑफ रेजोल्यूशन क्या बोलता है? लिमिट ऑफ रेजोल्यूशन इज द पॉइंट वेयर दे आर जस्ट स्टार्टेड टू सेपरेट. तो ये पॉइंट है ना, यहां पे वो सेपरेट होना चालू हुआ. इसके पहले क्या था? वो तो कोइंसाइड ही हो रहे थे, which was unresolved case. So this is the point where they started separating. So this is the formula which is for limit of resolution, means they just start separating themselves or they just start getting distinctly visible separately. So that is why limit of resolution ka formula is given by this. But this formula is when the distance is very less between the instrument and the particular objects. But what if the distance is comparatively higher? What if the distance is comparatively considerable, which is this distance? So what will be the total separation? Then it will be given by d into d theta. So this is the total formula, which is d lambda by a. And this is the distance of first minimum from the center. If it is at this distance d. नहीं तो कितना था? ये था. Clear, नीरज? Okay. Now, so this was for the first point when the two linear objects are considered. Once again, linear objects means what? Like a slit. So this is one slit and this is another slit which we have. If we are to say in the form of wave fronts, these objects give you linear wavefront, मतलब plane wavefront मिलता है, right? So that's why we are considering linear objects. Now, if we are to consider another type of objects which we have, again we have two objects. Now they are point objects. Means this is one object and this is another object. So when they act as a secondary source, now what will happen? In previous case, we were getting plane wavefront. In this particular case, we will get a spherical wavefront. Just to give you a difference between last one and this one. Now, in this particular case, now what will happen? Generally, whenever we look through any optical instrument, most commonly microscopes and telescopes which we have, generally the objects will be viewed closer or similar to the point objects rather than considering them as a linear objects, right? So the diffraction pattern of them, we already know how the diffraction pattern generally for point object it looks like. It looks like concentric circles or concentric discs or concentric rings, what we can say. Okay. So when we are looking from a microscope, when we are looking from a telescope, what happens? The objects is similar to those point objects, giving us the diffraction pattern in the form of discs or rings. So this particular pattern, obviously the concentric circles which we get, concentric rings बोल सकते हैं, disc बोल सकते हैं. Okay, I think I do have the image over here. Now this particular diffraction pattern, this particular arrangement is called as Aries ring or Aries discs for that pattern. Okay, with a central bright point or central dark point depending on what is the situation. Generally it's a central bright point which we have. I don't know why dark is given. Central bright point. Okay. So this is how the diffraction pattern it looks like in case of a point object. Notice the center point or the center ring or center disk we have. It's a bright disk followed by a small dark disk. Again you have a bright disk or bright ring followed by a small dark ring, again bright ring, again dark ring, so on and so forth. So this pattern of rings or discs or points for that matter, we can call them as airy discs or airy rings. And this is how it is shown in this particular diagram. Okay. Now, this particular Aries discs, obviously ये जो diagram है, this is the actual photo which we have of the actual diffraction pattern which was found out. These are the real airy discs which when passed through 90 micrometer pinhole, these are the rings of diffraction which are formed. Okay, and the minimum separation between them on that particular screen is the ring, is the radius of first dark ring. मतलब separation कितना होगा? ये first dark ring है, उसका radius, ये ring का radius will be the separation between the images on that particular screen. Okay. Now I do have actual photographs of airy disc or airy rings. It looks something like this. Okay. So you can see you have central bright ring, उसके बाद dark ring, वापस bright ring, comparatively brighter, then dark, so on and so forth. Again you can see bright, then एक dark band है, वापस से bright ring है, वापस से dark ring है, so on and so forth. So these rings or discs or circles, whatever we can say, they are called as Aries rings or discs or circles. Clear? Any doubts till this point? Bolo yes or no? Shubham, yes, you can try this at home, but I'm not sure whether it will be properly visible or not, because again, we need, try करके देखो, शायद मिलेगा, I'm not sure. Clearly visible नहीं होगा, but शायद मिल सकता है. एक कार्डबोर्ड लो, छोटू सा होल बना उसमें और टॉर्च से करके चेक करके देखो. क्लोज इनफ मिलेगा, एग्जैक्टली नहीं मिलेगा. Okay, now good. Now moving forward. So these are the actual practical images for these discs which we have. Now let's start with the resolving power for a microscope. Now obviously we are considering a compound microscope over here. So we are going to utilize obviously not this diagram, but this diagram which we have. We'll understand what exactly it is given over here. Now most commonly two instruments, optical instruments which are used, one is a microscope, another is a telescope. Now you already know how the microscope it works. You already have studied them in your lower standard, in your 10th standard, in your 11th standard as well. So I'm not going into details of how microscope it works, but we are going to directly delve into the resolving power of microscope. Now, in case of the resolving power in this particular diagram, this diagram obviously I've directly taken from your textbook. What we have over here, we consider 2 point objects O and O dash, which are separated by the distance A between them. Okay, so this is one point object O dash, another point object O. What is the separation between them? It is considered as A. AB, this is one lens. It acts as the objective of the microscope. Now, in case of the objective, when we consider the medium which is between the object and the objective, it is of refractive index n. Once again, this is the objects which we have, this is the objective which we have, the medium which is present in between has the refractive index, assume karenge n hai. Okay, now in this particular case, the wavelength which we are assuming is lambda n. Okay, why lambda n? N is the refractive index of that medium. So the wavelength of light which is emitted by source in that medium whose refractive index is n, that's why we are considering lambda n. What another thing we need to consider in this case? The angular separation between the objects. Angular separation, not the linear separation. The angular separation between them is 2 alpha, which is given over here. The separation between them angular on an angular level, and as a result we get the diffraction pattern in the form of I and I dash. So we have two objects, obviously we are going to get two diffraction patterns in the form of Aries discs. Why? Because they are point objects we have considered, and point objects they give you a diffraction pattern of Aries discs. So I and I dash, they are considered to be diffraction patterns, to be precise the centers of the diffraction pattern, which is formed due to objects O and O dash. Okay, and when we consider that this is which is formed on the screen, generally we consider that the screen is at a very large distance, very long distance, effectively, theoretically speaking, considering them at infinity. Okay, now let's understand. So this is the condition which we have for this particular microscope, and how to find out resolution of that or resolving power of that, that is what we are considering. Okay, so now when we consider, we are going to apply, when we consider microscope, we are going to apply Rayleigh's criteria once again. So as per Rayleigh's criteria क्या बोलता है? That the first ring due to O dash should coincide with I, and from O should coincide with I dash. Once again, to back up a little bit, what Rayleigh's criteria says. Rayleigh's criteria क्या बोलता है? First का minimum should coincide with second का maximum. So here, as per Rayleigh's criteria, the first dark ring due to O dash should coincide with I. मतलब O dash से जो फॉर्म हुआ है वो I को coincide होना चाहिए, एंड ओ से जो फॉर्म हुआ है वो आई डैश को कोइंसाइड होना चाहिए, फर्स्ट विथ सेकेंड, तो सेकेंड विथ फर्स्ट ऑब्वियसली. ओके, अभी now when we consider how the illumination will look like, then it is dependent on obviously the path difference. The nature of illumination means how bright or how dark the point will be, उसको बोलते हैं हम लोग nature of illumination. Again, whether the point will be dark or whether the point will be bright, वो कौन डिसाइड करेगा? Effective path difference. So at point I, we can consider the paths of extreme rays can be considered from O dash. Obviously, we can consider path of extreme rays will be O dash A I and O dash B I. So once again, O dash A I, that is one path through which the light is coming from O dash. Second path कौन सा है? O dash B I. So these are the two paths through which a ray of light will come to I from O dash. Okay. Any doubts till this point? Polar yes or no? Okay, good. So let's take our analysis further. So this is the path from O dash to I. But now what we know, that when we consider point I is coincident or symmetric with respect to point O. Point I is coincident with point O, or it is symmetric with point O. And O से path क्या मिलेगा हम लोगों को? Or the total path what we will get? It will be AI, which is equal to BI since it is symmetric. So what we can say the actual path difference is? Actual path difference is O dash B minus O dash A. Once again, just to clarify, from O dash to I, path कैसा था? O dash A and then A to I. This was one path. Another path was O dash to B and then B to I. This was another path. But अभी क्या है? ये जो A dash I है, A dash I is equal to B dash I. Sorry, AI is equal to BI. क्यों? Because I तो symmetric है from O. तो ये पॉइंट से सिमेट्रिक है, इसलिए AI will be equal to BI, right? More or less making it like an isosceles triangle. तो पाथ डिफरेंस क्या होगा? एक्चुअल डिफरेंस कहां पे आएगा? एक्चुअल डिफरेंस आएगा O dash B minus O dash A में. So this is the actual path difference when a light goes from O dash to I. And from diagram, कौन सा? अभी ये वाला नहीं, अभी ये diagram, from this particular diagram we can say that path difference O dash A minus O dash B is actually, geometrically speaking, can be given as D O dash, मतलब ये D O dash plus O dash C. एंड पाथ डिफरेंस का फॉर्मूला हम लोगों को पता है. पाथ डिफरेंस क्या होता है? A sin थीटा विच इज इक्वल टू n लैम्बडा. बट यहाँ पे दो है, दैट्स व्हाई व्हाट वी कंसीडर 2a sin, और एंगल कितना है? अल्फा. एंड दिस इज व्हाट वी कॉल इट एज इक्वेशन 1. बोल रही any doubts till this particular point? बोलो रही yes or no? ये 5 डिफरेंस वाला सुजल, हाँ ओके, ये डायग्राम को देख, अपने को 5 डिफरेंस क्या मिला, ओ बी ओ डैश बी माइनस ओ डैश ए. So geometrically we can consider this as d o dash plus c o dash. ये टोटल पाथ डिफरेंस मिलेगा. बेसिक ज्योमेट्री डी ओ डैश कितना आएगा, ये जो है ओ डैश और ओ, ये डिस्टेंस है अपना ए. ओके समझ रहे हैं, बोलो ये सुनो. ओके और ये जो एंगल है यहाँ पे, ये एंगल है अल्फा, क्योंकि टोटल 2 अल्फा था, उसका पार्ट आता है ये वाला अल्फा आता है, ये वाला अल्फा आता है. ओके सो इन दिस पर्टिकुलर केस अगर हम लोग ये कंसिडर करेंगे डी ओ डैश साइन अल्फा, क्या मिलेगा हम लोगों को, डी ओ डैश अपॉन ए. तो डी ओ डैश क्या मिलेगा हम लोगों को, ए साइन अल्फा. सेकेंडली सेम गोज ओवर हियर, ओ डैश सी, ओ डैश सी क्या मिलेगा हम लोगों को, साइन अल्फा, यहाँ पे क्या मिलेगा, ओ डैश सी अपॉन ए. सो व्हाट वी विल गेट, ओ डैश सी एज ए साइन अल्फा. तो ए साइन अल्फा और ए साइन अल्फा को ऐड करेंगे तो क्या मिलेगा हम लोगों को, 2a साइन अल्फा. ये हो गया ज्योमेट्री से. इफ वी कंसिडर पाथ डिफरेंस का फॉर्मूला इन डिफ्रैक्शन व्हिच वी हैव सीन, पाथ डिफरेंस का क्या आता है फॉर्मूला, a sin अल्फा इज इक्वल टू n लैम्डा ना. तो यहाँ पे 2 है इसलिए दोनों को ऐड किया तो 2a sin अल्फा मिला हम लोगों को. ओके सुजल, ठीक है. So this path difference, this equation is going to decide now which particular ring or which particular point has been formed, whether it is a bright point or whether it is a dark point. Okay now microscope. Now when we look through a microscope, compound microscope for that matter, the objects which we have, the people who have biology, they might have seen through a compound microscope. They, or even in your school days you might have seen some slides, some microorganism, paramecia, amoeba, maybe here and there, at least you have seen through it. So whatever object we are looking under a microscope, generally speaking, is not a self-illuminated object. It is not a primary source which we are looking under a microscope. Okay, very rarely we have a primary source which we look under a microscope. Otherwise what we have secondary sources, means they're illuminated from some other source. So that is the part which we are considering when we have the objects which are non-luminous or the dark object. Just like I told you, we don't usually see illuminated object or self-luminous object. Self-luminous matlab kya, tube light. Tube light is a self-luminous object, right? If we consider a bulb, it's a self-luminous object. Sun is a self-luminous object. Okay, These objects are, or the objects like them are not observed, but non-luminous objects which are illuminated by some external source, they are generally observed. So when we consider that illumination is not straight. I hope you know how it works. So it is generally oblique. This particular mirror, which is at the base of compound microscope, what it does, here is the part where the slide is kept. So you can see the mirror is thoda sa teda hai. So when the ray comes here, this is how the ray it goes, which gets reflected from the mirror. And ये जो आता है वो straight नहीं आ रहा है ना, थोड़ा टेढ़ा आ रहा है, angle में आ रहा है. You have to adjust this mirror in order to get a proper illumination. So when we consider this illumination, because of this, what basically happens, the objects they're considered to be point objects. And because of point objects, it produce Aries rings in the diffraction pattern. Okay. So that is how we are looking through it. Now, obviously, when you are looking through something, what you are looking through, you're looking through an eyepiece. So, in this particular, okay, in this particular case, I don't have any other color, beta. Black is in this particular case, what happens? Generally, the eye lens or eyepiece, what we say, is filled with some transparent material in order to adjust the refraction of this incident light which we have. So, in this case, what we have, the wavelength of incident light will be, the wavelength of incident light will be given as lambda n, which is lambda upon n. Where once again, what is this n? N is the refractive index of this transparent material. So, lambda n is the wavelength of light which is in that particular transparent material. लैम्बडा क्या है? इट्स वेवलेंथ इन एयर, नॉर्मल जो हम लोग नॉर्मली यूज करते हैं when there is no other medium present, and n obviously the refractive index of that medium. So in this particular setup, what we got, we have first non-luminous object which is illuminated by some external source. That external source, obviously it is not straight, it is oblique, it is slanting, thoda sa teda hai. Third point, objects are point objects, giving us the Aries discs or Aries rings in the diffraction pattern. Fourth point, eyepiece, it is filled with transparent material, giving us the wavelength as lambda n, n being the refractive index of medium. So in this particular setup, if we consider the path difference of the first dark ring, path difference क्या होता है first dark ring का? Path difference, just like we have said, it can be given as lambda n as equal to the length of first wave. वो कितना होगा? Wavelength, which is lambda n. So now we are using first equation. कौन सा वाला? Path difference we have found out, which is 2a sin lambda. We can write 2a sin lambda, which is equal to lambda n. But how much is lambda n? It is lambda upon n. So after rearranging, we can write a, which is equal to lambda upon 2n into sine alpha. So this 2 and sine alpha, when go to other side, they become, or they come in denominator. We can call it as 2 into na. What is na? It is not applicable. It is called as numerical aperture. Now, what is numerical aperture? N sine alpha, or to be precise, numerical aperture means the mathematical or numerical value of the lens or the size of the lens. उसको बोलते हैं हम लोग numerical aperture. So this A is the limit of resolution which we get for this particular setup. Now we know resolving power kya hai? Given by R, it is a reciprocal of limit of resolution, which is 1 upon A. So what will be the resolving power? Resolving power, it is given as 2 Na upon lambda. Once again, what is Na? Na is the numerical aperture, means the mathematical or value of the size of that particular lens which is being used. Clear? Any doubts till this particular point? Bolo yes or no? Okay, good. So this once again is for non-luminous objects. Okay. What is yes or no? Okay, good. So this is once again for non-luminescent objects. What if by chance we have some luminescent object, self-luminous point object is what we are actually finding, or is what we are actually looking at. Now obviously we know that there are no self-luminous objects which we have which needs microscope, right? For example, tube light, उसको देखने के लिए microscope की जरूरत है नहीं अपने को, right? Or if we need to see sunlight, again you don't need a microscope for that. If we have a bulb, you don't need a microscope for that. So are there any microscopic organisms which have self-luminescence or self-luminous for that matter? Yes, there is a separate division of biology which is dedicated to the study of bioluminescence. Means there are certain creatures, there are certain organisms and microorganisms which has these characteristics of producing light. One of the best example which you are familiar with are fireflies. Marathit jala kazwa म्हणतात. It has a property of self-luminescence. There are other different types of beetles. There are different types of caterpillars which have this characteristic. There are different types of fungi, mushrooms, bacteria, bioluminescent bacteria बोलते हैं उनको. They have these particular characteristics of producing light. So by chance, if you are looking at these type of objects, means they have their own light. तो अपने को additional light ऐसा लगेगा नहीं वहाँ पे. We do use them, but we won't need it much, like previous case. So here as well, we consider that these are the point objects. Keep that in mind. That is what is important to us. So here also, we apply the concept of airy discs only, because obviously we have point objects which we are looking under a microscope. So we apply this airy discs or airy rings concept to the Fraunhofer diffraction. Now we have already seen Fraunhofer diffraction for two self-luminescent point objects. So we have the big huge derivation of that. What we are interested in, where the first ring is formed, first dark ring to be precise. So the difference between the extreme rays at first dark ring is given by 1.22 lambda. सिर्फ इतना याद रखो, इसका डेरिवेशन है, but we are not going to details of that. It's neither given in your books nor it is given in any other books for that matter for your level. So now applying this particular concept, previously what we had for just resolved case, we have 2 sine alpha which is equal to lambda n. But now here the factor which we have, the additional factor of 1.22. So now for just resolved case, we are going to apply this once again. So now what we get for self-luminescent objects, we get 2a sine alpha which is equal to 1.22 into lambda n. Notice this factor. So just like before, what we will get, a which is equal to, the only additional thing which we have is 1.22 lambda n upon 2 sine alpha. Lambda n same as that of before, which is lambda upon n. So let's incorporate that. So this lambda n is given by this lambda upon n, just like previous case. If we want to simplify, we can write 2 into 2 ones are, and when we divide this, we get 0.61. So we get 0.61 lambda upon n sine alpha. And we know इसको हम लोग क्या बोलते हैं? We call this as numerical aperture, NA. This is our limit of resolution. So resolving power is reciprocal of that, which gives us NA upon 0.61 lambda. And obviously, we know that this is the resolving power, and for better resolution, A, which is the distance between the point objects, should be as minimum as possible. So we get better resolving power or resolution for that matter. Okay. Any doubts in this? Bolo re yes or no? Okay, good. So once again, looking at time, we have just shy of 2 minutes for 6. So today we'll stop over here. I hope you have understood everything. Please go through this entire part. Once again, we are almost at the end of this particular chapter. Theoretically speaking, we still have lots of numericals and entrance numericals to get to. So please attend all the lectures. Here on onwards, the small theory part which is remaining, and maybe in couple of lectures we'll be starting with numericals. Okay, so chalo.